In the hush of the night skies, a creature stirs, delicate, elusive, and masterful. The bumblebee bat, weighing no more than 2 paper clips, weaves effortlessly through the darkness, with not a single ray of light to guide it. It hunts, it evades, it survives. Its secret? A marvel of nature. Echolocation. By sensing the faintest echoes and discerning subtle differences between the signals reaching each ear, a bat can detect obstacles no wider than a pencil lead. An exquisite ballet of biology and sound. Inspired by this natural mastery, we bring echolocation to the realm of machines. Lightweight, aerial robots no larger than the palm of a hand. In the face of snow, smoke, or complete darkness, they navigate with astonishing agility using but a whisper of power. Just 1 milliwatt of ultrasonic sensing, entirely self-contained, without GPS or external infrastructure. Yet, this is no simple task. On board, the spinning propellers of the robot generate a cacophony of ultrasonic noise, enough to entirely mask the signal. To make the ultrasonic world audible to us, we transform echoes into sound. Each obstacle becomes a tone. Its loudness reflects echo strength, its pitch, the distance. Together, these tones form a soundscape, a glimpse into how the robot perceives its surroundings. To rise above this acoustic turmoil, we propose 2 elegant solutions. First, a physical shield, an acoustic cloak of sorts, dampening the noise before it reaches the sensor. As we demonstrate, the difference is striking. But shielding alone is not enough. Sound, as with all things in nature, carries patterns. And so, we harness temporal coherence, the rhythm hidden in the echoes, to reconstruct clarity from chaos, introducing Saranga, a neural network that listens, learns, and reveals. Fed with a sequence of echoes, our Saranga neural network discerns the signatures of obstacles, a crisp, impulse-like edge revealing not only their presence, but their distance. Trained entirely in simulation, it steps boldly into the real world, requiring no fine-tuning and no retraining. We tested Saranga across 9 challenging environments on a custom-built, palm-sized quadrotor. It navigates deftly, even through transparent filaments thinner than a strand of human hair, objects unseen by stereo vision, LIDAR, and radar, each consuming 1,000 times the power. 2 wide field-of-view ultrasonic sensors transmit and listen, and Saranga interprets the returning echoes. Using time of flight and bilateration, it pinpoints obstacles with a precision of 10 centimeters. Darkness does not deter it, nor snow, nor smoke. In each condition, it flies true. Even slender obstacles no more than 10 millimeters wide and made of diverse materials are deftly avoided, with success rates of 100, 77, 90, and 82% respectively. Even under the gentle sway of forest breezes, gusting up to 15 kilometers per hour, it darts between trees with an average success rate of 85%. These are not open spaces, but tangled, dynamic environments with varying tree densities where branches shift and light deceives. Yet, guided by echoes alone, the robot navigates with an instinct almost animal in nature, a testament to the power of minimalist design and the elegance of sound. The implications are profound. In forest fires, in disaster zones, in places where vision fails, this tiny machine, with its 4-gram sensing payload and minuscule energy draw of just 1.2 milliwatts, could one day lead the way, saving lives where others cannot venture. We have made Saranga open source, its code, its hardware, its vision, and we hope, like the bat that inspired us, it guides the next generation of bio-inspired, resilient, and minimalist perception systems toward safer, more reliable autonomy.